know and get familiar with our whole system. So the purpose of the platform is to provide a place for circuit design to happen in a framework that includes all aspects of circuit design, as in chip design, integrated circuits for chips from end to end. And this is the important part, without the need for an NDA. This gives designers or prospective designers a way to get a feel for how a particular circuit works on a particular foundry process node without having to do the work of setting up design kits or committing to expensive software toolchains. Ultimately, designs will end up as layout in GDS format for fabrication. Once a design gets to this final stage, anyone who wants to have this intellectual property in hand may go sign the appropriate NDAs with the foundry for access to this data. And then they can get that data and do whatever they want with it. But up to that point, designs can be made publicly accessible in a format that doesn't reveal proprietary foundry data, and circuits can be viewed in this form and evaluated on the basis of their characterization. This is the vision that we have for the eFabless marketplace. I'm going to take myself off the webcam now until the end so that I can share the eFabless website while I talk about the platform. Much of what I'm saying here we have written up on our site. If you go from our main website to the links customers or community, then follow the link to how it works, you will get a quick overview of this marketplace idea. If here you go to rulebook and follow the link down to FAQ, you'll get a more detailed explanation of all these subjects that goes into a lot more detail than I have time for here. In a way, our design model is partly modeled after Moses in Southern California, which is similar to Europractice if you live in Europe. That is a broker for designs for filling foundry shuttle runs. Moses promotes, and has for something like 30 years, circuit layout that uses obfuscation of proprietary foundry rules by having scalable CMOS-like technology, which is a set of conservative rules that makes it easier to make designs compatible over a set of process feature sizes. But it also hides the vendor rules to an extent that the vendor, the foundry, doesn't care if those layouts are made public because nothing about the process can be reverse engineered from them. We promote the same idea as a way to get designers to be able to do layout and to have that layout, at least in that conservative rule format, available to the public. Unlike Moses, though, our platform is end-to-end, and it includes schematic design, extraction, simulation, and characterization. This is something that can only be done by having cloud-based services running on a remote platform with virtual hosts, where we can make sure that the foundry information can be divided into public and private areas with strict access control. This allows, for example, schematics to be built with publicly accessible symbol views, but with hidden device models. The designer sees the symbols, but the simulator will see the models. The simulations are run on a process that has an elevated access privilege compared to the user who's running the simulation, using the user's schematic, but pulling models from protected areas of the platform. Users get to make changes to their designs and see the results of those changes without knowing the specific foundry model details. Likewise, the user can build layouts, and the tools extract devices and parasitics and perform characterization on layout extracted results without the user having any detailed knowledge of the process specifications, other than, as mentioned before, some design rules that are either already publicly available or that have been relaxed a bit compared to the actual foundry rules. Not to bore you too much with talking points, I'll go move to the dashboard up here and show you the main page that gets you to the various parts of the system that you'll need for doing the challenge. I'm going to let Jay go through this in a minute. Here you'll see a few additional links that I get to use as staff, so it won't look exactly like what you see. You will see here Learn and Practice, which is how you get to our online course offerings. I'm going to go over to Open Challenges and click on here on View Detailed Specifications to get to our challenge spec sheet. Now, the heart of the eFabless platform is something we call ACE, or the Automatic Characterization Engine. It's something that we developed internally here at eFabless. The purpose of the software is for a user or company or foundry to specify a circuit, or maybe an entire chip, in a format in a formal way that looks like a product data sheet, but precisely captures the critical parameters of interest for that circuit and completely defines the conditions under which each parameter is tested. Here you're looking at just such a spec sheet. This is the one that I drew up for the challenge that is based on input from XFAB. Not only does this provide a firm framework for running characterization simulations, but it ensures that the finished product comes with a data sheet that is complete and unambiguous. If this spec sheet is for a challenge like this one here, this information tells the designer exactly how the circuit must operate, and it can be used during the design process to gauge how well the circuit behaves relative to the specifications. Jay will shortly describe the format in a bit more detail, but the point here is that the page is fully describing a circuit, and you can view it on the web here as a way to determine if this challenge is something that you know how to design and you can meet all these specs for. But also it shows up on the platform as an application where you do the design, the same data here, but presented in a way where you can see how your design in progress is stacking up against the spec. We have yet another web page view where this same data set is shown with the characterization results from your design, including all these plots. And for those of us checking challenge results, that is an indication of any parameters that you have in your design that may not meet spec. Characterization involves running lots of short simulations, largely operating point, DC and AC analyses over all these conditions that are specified in this data sheet. The designer can run these simulations one at a time, but to get the official challenge result, your design will be packaged up and shipped off to a remote server that runs the official characterization. That will be the version that ends up on the eFabless marketplace and which we use to judge against other entries to determine who is the challenge winner. I'd like to stress the difference between a local characterization, which is done on the design platform, and the official ACE characterization, which is done by pressing a submit button. That one is your final answer, although you can submit updates as necessary. Normally, you should be running local characterization only while you are working on a design. Jay will show you how this works on the platform. Now, going back to the open source software thing, eFabless is not necessarily limited to hosting only open source software. In fact, we don't in the case of the simulation waveform viewer. But we are dedicated to providing tools that are accessible to everyone on our platform. Because all these tools have a learning curve, sometimes a pretty steep one, we provide help in the form of how-to documents and videos for those users needing to climb that learning curve on these tools. You can get to all this information from the main website page here. Yes, come up. There we go. By clicking on Community and then following the link to Knowledge Base. We want to give the users a walkthrough of every step of the challenge design process and how to get through it successfully. This is a fairly sparse list at the moment, but we are still adding to them and should have a pretty comprehensive set of them up by the time the challenge is fully underway. Information about open source tools is also available on the internet. Sometimes it can be found within the tool itself on our platform. And as always, we have a help desk tab available in the design workspace. That is, if all else fails, you can come talk directly to us. For schematic capture, we use Steve Rubin's Electric. For layout and verification, we use Magic and NetGen for my own open circuit design. For simulation, we use ngSpice. Not part of the first challenge, but available soon on the platform is Mohammed Shalan's Cloud V for digital synthesis, and that uses Clifford Wolf's Yosis for Verilog synthesis and QFlow and QRouter for the back-end routing. We have one closed source tool called SimProbe, which is for viewing waveforms during schematic design. The framework that holds all these tools together is comprised of a number of scripts and user interfaces using the ACE, the characterization engine that I mentioned earlier, and a project manager, as well as the whole web-based platform that I've shown you some of, which includes documentation, the challenge page for viewing and accepting design challenges, a marketplace for displaying challenge results, and ultimately a place where users of the eFabless platform could buy and sell IP or even post their own design challenges. back to the main page. For our first official challenge, we are pleased to be able to work with XFAB, a foundry that is well known for being accessible and friendly to work with, very open in its information for designers, and it's renowned for its specialty analog processes. XFAB has defined the scope of this initial challenge, and they've offered specifications for a low-power bandgap reference circuit to be designed on the XH035 0.35 micron process. This challenge will be, in a word, challenging due to the constraint of using only the most basic foundry process option. We are allowing all device models available in that base process option and no others. These devices are built into the schematic and layout design kits. The scope of the challenge is here, which is the spec sheet that I showed you earlier. And if I go back to that page, down at the bottom, we have the monetary prizes being offered, which is the incentive for the amount of work that you're going to have to put into this challenge to get a design done. When you register with eFabless, or at least when you accept a challenge, each of you gets an online cloud-based virtual computing workspace where you can do your designing and simulation. That can be gotten to from the dashboard and the toolbox. We call this workspace Open Galaxy, and you get there through this Design Verify link. This and the ACE results are what you will see for the challenge. These other links, let me go back there. These other links here that you saw are a sneak preview of things that we will be bringing onto the platform in due time. So here is the Open Galaxy workspace. This workspace is restricted to challenges. It may be used for designs of any purpose. It's not restricted to challenges. You may use it for designs of any purpose, and it makes all supported software available. If you go down to the bottom corner here, the desktop toolbar has an eFabless icon that launches the project manager, where the user can see all the projects that they're working on and launch all the main applications needed for the circuit design. This environment is a standard Linux OS, and in addition to the project manager, you have the ability to open a terminal and to type in your standard Linux commands like cd. Now I cannot reach it. Am I sharing my screen right now? Oh, I think I'm not. Can anybody tell me, can you see?
You are sure. Yeah, we can see your screen.
You saw me type CD there.
Yeah.
Okay, all right, sorry. I have too many windows up here. All right, but at this point, down in the workspace, I'm jumping a bit ahead, but I wanted to do that to explain what our platform is exactly and how it all fits together. So at this point, I'm going to invite Jay to walk through the process of accepting a challenge and show you how to get to this workspace for the first time, and how you will get to the tools you need to do your challenge design, and how you will submit that design back to the marketplace as your official competition entry. So at this point, I give the screen over to Jay.
Thank you, Tim.
Okay.
Hey, so my name is Jay, and I'll be leading you through the challenge overview from that is the designer's perspective. As Tim has already briefly mentioned about the challenge, we'll begin with first overviewing the challenge objectives, the challenge details, but what is more specific to a designer is the specifications. That's what is going to define who wants to accept the challenge and who wants to be out of it. Hopefully everyone will accept it because it's so exciting. So when you look at the challenge data sheet, at the very top section, we've got the challenge details like the name of the challenge owner, the process node that's available, which in this case is XFAB's low noise 0.35 micron technology. It also lists the name of the IP that is to be expected to be delivered. And next we have is the section called as pins. Now, pins is nothing but this section defines the standard pins names to be assigned to the deliverable package, which in case of schematic design is going to be a symbol with 6 pins, namely VBG, PD, and VDD3A, and the description associated to each pin named that the challenge owner has requested. And below this section, we've got global conditions. Now, these are known as global conditions for various target specifications that are listed below. The electrical parameters, which are the target specifications defined by the challenge owner. And for every electrical parameter like line regulation, load regulation, temperature coefficient, the target specifications defined by the challenge owner are enclosed in curly braces. And if you notice here, you've got another field called conditions. Now, this is what is known as the local conditions. Now, if you remember, we've got global conditions back here, which are common for all the electrical parameters.
Jay, I think we are not seeing your full screen.
Okay.
We are still on the
challenge. Yeah, we're on the challenge details. If you can share your other screen. Yeah,
All
there
right.
you go. Very good.
Is it still?
Yeah, now it is fine.
It's good.
So as you can see here, you've got electrical parameters. So you've got global conditions, which defines the standard, which are the common conditions for all the electrical parameters. And we've got local conditions by this collapsible menu item, which tells you the unique set of conditions specific for the given electrical parameter. And these are the electrical parameters set by the challenge owner. And finally, we've got physical parameters, which are specific to layout defined by the challenge owner, like, for example, the area of the die size, the maximum area of die size, as well as the width and the length of the design that a designer needs to constrain their design for bandgap IP. So we'll go ahead and hit accept. And this is one step closer to accepting the challenge officially. And at this stage, we've got terms and conditions, which are defined in a very lucid and a simpler language, so that designer can go over it, understand the process, as well as the terms and conditions involved with a given challenge. And
Jay, sorry for interruption one more time.
Yeah.
I don't think we see your screen though.
Okay.
Okay, now it came up. Anyways.
All right. I'm just going to go over and share the whole desktop. Okay. So at this stage, we've got the terms and conditions, and we encourage users to go over the entire terms and conditions right from top to bottom. And it's just a quick 5 or 10 minute read to ensure that you comply with the terms and conditions of eFabless and the challenge owner. And once we do that, we've got the quick check boxes to accept the terms and conditions. And when we hit confirm, that's it. That's when we are officially part of this challenge, which is what I call as the first design hackathon or designathon for IC designers. Now, at this point, a user can either go back to challenge overview to revise the challenge specs, or you can simply go to the Open Galaxy environment, which is the design space for the designer to get started with schematic design. So we'll go ahead and hit design and verify to open our Open Galaxy design space. And now the first thing that I'm going to do is open the project manager. Now, if you look at the project manager, you've got two fields, namely the imports and the projects. Now, once a designer has accepted the project, all the project files pertaining to that challenge are held up here in pending imports. And a designer needs to copy over these project files into its into his local design space by hitting import as. And at this point, we've got all the project files needed to get started with basic schematic design into the local user design space. Now we'll go ahead and edit schematic to open the electric schematic editor tool. And as you may have noticed, some of you might have noticed, familiar with electric, the interface looks the same, but it is explicitly customized to match with the challenge owner's PDK and give designers a unique set of experience to play around with devices and basic analysis. Now, the first thing that you might notice while opening the edit schematic editor is the library called xbg_13lc_v01, which in this case was the name of the IP from the challenge datasheet. And this is the challenge library. That is what we call it as the challenge library. And it is shipped by default with the symbol view of the challenge with set of the standard pins defined in the challenge datasheet. Now, for user or designer sanity, we encourage users not to modify this library. Instead, we ask users to create a new local library by the name of something called as my initial design library. And within this newly created design library, we'll create a new cell called as for our working schematic, my initial working schematic, or we can say it as design. And at this stage, we have a new library and a new blank schematic design. Now, in order to ensure that you have a blank schematic and to get started with the basic schematic design, we'll be shipping users with two set of libraries, namely the tech_ngspice library, which contains all the independent sources and set of basic analysis required for schematic simulations, as well as the library for PDK, which is nothing but tech_EFX035A, XFAB's 0.35 micron technology, specific for this challenge. And as you can see here, these are the available devices to users to create their schematic and get started with their challenge. We'll go ahead and instantiate a device by clicking on the device and simply dragging and dropping the device into our blank schematic. Now, at this stage, I would like to add one more thing, which is if a designer is unaware of the foundry specific details of the PDK that is being shipped, the designer can simply go to documentation, process, and access foundry specific datasheet to enumerate and to decide what devices would fit best for their initial schematic design. And at this stage, I'm going to speed up and create a basic characterization schematic by adding voltage sources from tech_ngspice library and a current probe. Now, you might have noticed some of the SPICE enthusiasts might have noticed that we've got something called as current probe. Well, it's to simplify the user experience while designing circuits, much like they might have used some other leading EDA tools. Now, once we have the basic set of voltages and current probes, voltage sources and current probe. We are going to add a global ground by heading over to the tab called Components and dragging and dropping the ground symbol into our schematic. And next, I'm going to simply use my copy bind key to copy over voltage source, ground pins, now at this stage, I'm going to go ahead and wire up my schematic. And the way to do that in electric is you have to simply left click on the source node and right click on the destination node. It's that simple. If you have a multi-path route, right click on the source node, left click on the source node, right click on the schematic to create a multi-path wiring. I mean, this is way simpler than some of the other user interfaces wherein you have to select the wire mode and wire up your devices. And obviously, the way a designer wires up their device and places these instances is completely different from. And at this point, I'm going to rename this current probe as drain probe and leave the name of nets as default as net@2. A user or a designer can obviously rename the nets and wires to make sure that the design is more organized and specific. And now I will perform a basic DC sweep. For that, I'll go under tech_ngspice library to look at the basic set of analysis shipped by eFabless to perform basic set of small signal analysis in a click of a button and drag of a mouse click. And as you can see, I have imported sweep DC analysis back in my schematic. And I'm intending to sweep my gate to source voltage from 0 to 3.3 volts with 100 millivolts increments. And all I have to do is add the right instance or the right independent source that needs to be swept. So I'll look at the name of the instance, which at this point is VDC@0. Make the changes in the analysis window. VVDC@0. Hit apply. Okay. Change the VDD from 1 to 3.3, which is standard for the NMOS cell of this PDK, this technology. And finally, I'm just one last step up before I can hit the simulation button. Now, I'll head over back to the PDK library and add drag and drop analysis process corners, which contains the process corners, the information for process corners for the ngSpice to perform the set of simulations. So in this case, the process corner that we'll be running through is TM, which is the typical case by default. And at this stage, I'm going to save my library. And I'll hit the simulation button. Oops, it seems like we have a simulation error.
Yes, I recall you saying that you wanted an error. You don't have your bulk
bias.
node.
Yeah.
See, that's a good catch. All right. Another simulation error.
I think that this is the same error we were coming up with earlier today. Did you have a saved version of this that worked?
Yes, but it got overwritten by the new challenge accept.
Jake, can
I'm pretty sure it's a small hiccup. I mean, I'll have to cross-check my net connections. That's it.
Jay, one request I have.
Yeah.
We want to allow time for questions from the
Sure.
members.
So let me just sweep ahead. I mean, we can obviously self-analyze what is the net that is causing me this problem. I'm pretty sure it's a hiccup from my end. So I'll anyways save this as my initial design library. And now I'm going to sweep through to the point when a designer has finally decided that he has a final iteration of his bandgap design and he's just a step closer to, submitting his design before a day or two before his submission, a schematic design submission. So at this stage, I'm going to open up a demo library called My Finished Design. And within this library called My Finished Design, I've got something called as final design _1, which contains a demo schematic, which not necessarily is going to meet all the specifications set by the challenge owner, but it is something to illustrate and demonstrate how the ACE engine or the ACE characterization tool works, which is the heart and soul of this webinar. So at this stage, we'll move over to the challenge library and we'll open the symbol view of the deliverable IP or the deliverable package. Next, we are going to create a blank schematic that will map the pins inside the challenge IP symbol. We are going to close this window. It's just a confirmation to tell that, hey, a new schematic has been created. So at this stage, you might have noticed that we have a group cell that's been created. If I collapse this group cell, I've got not only my symbol, but also a blank schematic with a set of standard pins defined in the original datasheet, the challenge datasheet. Now at this stage, I'm gonna simply zoom out, use the hand tool, put it somewhere the top right corner, move over to my final design, which is my local working direct library and the schematic design that I might have iterated using SPICE simulations. And I'm gonna select my schematic, use the copy bind key, move over to the mapped schematic, and I'm going to place this my working schematic into this blank schematic defined by the challenge library. And at this stage, the designer needs to map any nets and wires in their design, in their custom design, with the nets and wires which are defined in the standard data sheet, which is right here. So as you can see, for example, VDD33A is nothing but the supply voltage high pin, and that needs to be mapped with the VDD of the designer's local design. And once we map all the pins with the nets in the schematic, we can just go ahead, save our design, and exit electric, and come back to the project manager to open our ACE characterization tool. So at this stage, I'm going to click back on the challenge challenge project, hit characterization button to open the ACE characterization tool. And this is what the ACE characterization tool looks like. I mean, so to give you a quick summary, the designed by the user, that the schematic that has been imported into the challenge library, okay, is hooked up to this characterization tool to perform and evaluate a designer's design and check back for the performance of the design that's being designed. So at this stage, I'm going to run a quick local simulation, namely the temperature coefficient. So I'm going to hit simulate. And so the schematic that we just added into the challenge library is going to be netlisted, and the ngSpice simulations are run locally to check for temperature coefficient. So the beauty of this characterization tool is that once a designer comes up with his final design, they don't have to go over the tedious process of defining test benches and adding those global and local conditions. ACE engine and ACE characterization tool takes care of it in quick of a moment. And if you look back here, since it's a demo schematic of bandgap IP for illustration, and as I said that it might not meet some of the specifications, we can actually see that the schematic designed by the user doesn't comply with the upper end of temperature coefficient requirement. So one of the other features of this characterization tool is that the user can also look back where exactly this design failed. So you can click on fail to give you a detailed report of the set of conditions under which this design was evaluated, as well as they can even sort the results to look for the conditions for which the design failed and the conditions where it didn't fail. So at this point, you can see that, you know, for the trim bit configuration of 1000 and typical case, that's the point until which the design performed reasonably well for the given set of target specifications. Now, another feature of the ACE design tool is it not only gives you information about the electrical parameters defined in the datasheet, but also some of these quick performance charts so that a designer can assess, like, where exactly their design stands. And so for this, I'm going to run a quick voltage bandgap output VBG versus VDD 3A test, which is nothing but the output voltage of the bandgap IP from the VBG pin versus variation in the supply voltage. And as you can see here, it's already simulated, and I can click on the done button to generate a chart which says how well my design performs, what's the output bandgap voltage over variation in the supply voltage. So as you can see, it is not only challenge owner friendly, but also designer friendly to get a quick overview of where exactly the designer's design stands in the schematic design process. Now, I'm just going to go over and hit the submit button. And what this submit button does is, so far what I've shown you here is nothing but local simulations. Now, as Tim pointed out, local simulations are different from global simulations. or the A simulations. When a designer decides to run simulations back here in the characterization tool, his design is simulated within the design space to give him a quick insight of where exactly his design stands. But if the designer decides that his designer is sufficient or meets the given set of conditions defined by the challenge owner, he can simply go down to the submit button to upload his design to eFabless marketplace, and at that stage his schematic gets uploaded to something what we call it as ACE engine, and the ACE engine internally evaluates the design for all set of electrical parameters as well as certain performance charts so that it could be evaluated and those results can be uploaded back into uh, ACE results, which is not only accessible by the designer in the eFabless toolbox called ACE results, but it is also available to challenge owner so that they can assess that designer's design and see where exactly the design stands amongst the pool of other designs that are being submitted by other challenge users.
Jay, if I may do a time check, I want to make sure that we cover
Yeah.
all the points and leave enough time for questions.
Okay.
So thank you for the demo. Tim, you want to take over and then we open up for questions?
Well, if Jay can very quickly just show the ACE results page, because that is important. It shows
Sure.
what it looks like at the end.
So from a designer's view, if I'm a designer, I've got ACE results, and this, if you can see here, currently the design is still being evaluated, but I'm going to go over and show you one of my previous iterations or previous submissions, which is this guy. And if I click on details, I not only get the entire data sheet, but I also get the electrical parameters and the current state where exactly my design stands against challenge owners' target specifications. And not only do I get to see that, I also get to see various performance charts as we discussed earlier. And this is not only helpful for the designer, but it is also helpful for the challenge owner to quickly evaluate what design is better than the others. Back over to you, Tim, so that you can finish up what we've discussed so far.
Okay, thank you very much, Jay. Yeah, I'm going to go ahead and put my face up again. Actually, right. So since this is our first challenge, we'll be bringing more and more capability for the system online, and we'll be doing that as the challenge progresses, and much of that's going to happen during the month of December. If you noticed, there was one thing missing from the view that you were given so far, and that's the whole method for layout. All of the layout tools right now are in the final stages of development. That's all going on behind the scenes, and that'll be rolled out in a few weeks. As a quick summary to give to you now, there will be a tool that is part of the project manager to translate the schematic netlist to a basic layout of unorganized devices, really a basic, and I mean really basic kind of schematic-driven layout. Manipulating device layout views and wiring them up will be the subject for some additional tutorials, and possibly we'll do another webinar on it. So stay tuned for that, and we'll let you know when that's coming and where to find the tutorials. For LVS, layout versus schematic verification, that will be done with NetGen using a new graphical interface for viewing and interpreting results. DRC, layout design rule verification, is supposed to be correct by design by using those conservative layout rules that I was talking about earlier. And that will, to some extent, prevent getting the most dense layout possible, but it will make the layout process very easy, even we hope for newcomers to the platform. Once a layout has been made and LVS has been verified, the whole ACE-based characterization process that Jay demonstrated can be repeated with the layout extracted netlist, and the final characterization will be performed on that circuit. So technically, we gave you the short view up to a kind of first stage submission. You will submit there after schematic design, but you will be returning to that after layout to submit the completed design, layout, and all. As is mentioned at the bottom of the challenge acceptance page, which you'll see if you read it carefully enough, which you should, a designer may forego the whole layout process if they're not familiar with the whole aspect of circuit design with the circuit layout. But if they do drop the layout part, they will have to take a penalty on the prize of $1,500 for a winning design that does not have a corresponding layout. We understand that there are engineers who don't know how to do the layout part, and we want a way for them to be part of the community as well. Otherwise, our community is going to get a lot smaller. So I'm going to end the seminar here, and we'll follow up by having me and Jay and Rajiv and possibly others of the eFabless team, if they're here and want to weigh in, field any questions that you may have. So thank you all for listening to this presentation, and thank you all for participating in the challenge, and above all, thank you all for believing in community-based design engineering, and best of luck with your designs.
Thanks, Tim.
Yeah.
Thank you so much. I really want to open up the forum for anyone who has questions, who may have tried our platform and may have encountered any problem. Please feel free to ask questions, give your feedback.
It's also quiet out there.
Hopefully people are finding unmute button. But in any case, I want to add that we will have follow-up seminars. We will also post the recording of this webinar on our website, so you can see it later. Feel free to reach out. Did we have a question? Sorry.
Yeah, I think someone did bring up Vadim. I hope I'm like pronouncing your name right. Yeah, so the question reads, in case, thank you for your presentation. Is it possible to make a sweep simulation for parameter of a MOSFET with? Yes, at this stage, we can quickly do that, and it involves a combination of Spice code as well as one of the analysis library, but we've got something really exciting. We are even trying to get a graphical user interface based 2D sweeps, which is nothing but you can not only perform DC simulations, but you can even iterate a parametric simulation around that DC sweep, wherein you can change device parameters like width, length, or maybe instance parameters that a user might wish for a given set of devices in the schematic. I hope I've answered your question, Vadim.
On the knowledge base page, there is a 1D sweep tutorial. Does that cover things like a width parameter change?
Not precisely. I mean, 1D sweep with device level interaction involves some set of Spice coding as well as 1D sweeps, and we want to make sure that users have a streamlined experience. So we are combining both of them and making something called as 2D sweep, and we are expected to deliver it, probably by the end of this week or probably next week. So we are pretty close with that aspect. Yeah.
I will add, I think we have the solution that we have. We will post it on the knowledge base. So we will put it up there, but we will follow up with our community and let everyone know that we have some answers on the knowledge base.
Yeah, and at this stage, I would like to add that we are fine-tuning and refining some of the knowledge base articles so that it fits in the best interest of this challenge. And it would be great if you can add, if you have any feature updates or feature suggestions that you as a designer would feel that, hey, this needs to be done or this needs to be added. it would be really great. Thank you.
Open for other questions. Okay, so I will, as I was mentioning, we will follow up with other webinars and we will make the announcement through emails.
Hello.
Yes. Is that Alexander? Okay.
I think that was Alfredo, Rajiv.
Okay. Alfred. Yeah. Go ahead, please. Alfredo, we are not able to hear, but in any case, I will follow up with you on an email. Just as in interest of time, I want to be conscious of everyone's time. Thank you again, everyone, for joining us on our very first webinar. We are excited about this challenge and the opportunity to work with you. We are always open for your feedback, your suggestions. So please keep them coming. Thank you again, everyone.
Yes, thanks for coming, and take care, everybody. And again, good luck with the challenge.
Okay, we'll end the meeting now.
Thank you. Bye.
Bye.
Bye-bye.
Thank you.